Hello, my name is Garcia, and for my STEM Fair project, I created a solar panel that aims itself towards the sun to increase its efficiency. My hypothesis is that a solar panel which can tilt to maintain a 90-degree angle with the sun will be more cost-effective than one which cannot move, because solar panels produce their peak power when the sun's rays hit the panel at a right angle. The first step of the build process was to research the parts I would need. Through the designing phase, I had decided that I would use one servo to rotate the solar panel. I would obviously need a solar panel to actually gather the energy, and I would need some sort of microcontroller just to program to control all of this while it's happening. I would make a frame out of scrap wood and hardware that I already had. When researching options for the solar panels, weight was a major factor since I would need a more powerful and more expensive servo to move heavier panels. I decided on the SoShine 6-watt panel shown in the bottom right on this slide because it is lightweight, has built-in mounting points, which is very useful, and it seemed decently constructed compared to some of the other options. A few of the other solar panels I had researched had misaligned cells within the panel. They looked all crooked, so I steered clear of those ones. And this panel also has a USB plug. It was made for charging a phone, but I could use this and a spare USB cable to easily measure the voltage and current of the panel. When researching microcontroller options, I quickly settled on an Arduino Uno because Arduino has the most documentation by far of any microcontroller I found, and this would be very useful for programming it. The Uno was inexpensive and could easily control most standard servos as well. Choosing a servo was definitely the most difficult decision I had to make in this phase because I have limited experience with them. I calculated the torque needed to rotate the solar panel about its edge if all of the mass were on the opposite edge, a scenario that would require much more torque than my actual use case. This calculation yielded about 35 ounce-inches of torque, so I selected a well-reviewed servo with 44 ounce-inches of torque that was within my price range. Once the parts had arrived and I had tested them, I got to work building them. So the first thing I did was build the wooden frame, and then after that I was able to bend this piece of brass and mount it to the included holes in the solar panel, and that curve was set so that it would fit around a wooden dowel and rotate. After I mounted that bracket, I secured the servo to the opposite side of the structure, and then the solar panel was hinged on the dowel and attached to the servo on the other end. After the servo was attached, I was able to mount the Arduino. It came with an included bracket, which was very convenient. And I did need to add a wooden spacer so that when the panel tilted the full 90 degrees, it would not interfere with the Arduino on the edge. For programming the Arduino, I went through several iterations of code, starting with a very simple program that just set the position of the solar panel to get a handle on how to control it within the program. From there, I moved on to a slightly more complex program that would just work for a day. So if you start it right at the beginning of the day, it would just move gradually throughout the day on a per second basis. From there, I moved with lots of bug fixing to this final version of the code. It used a public template to keep track of the time. So you would input the initial time whenever you're starting it, and it would theoretically run for a whole year, and even longer actually, by calculating the sunrise and sunset time of each day based on which day it was, what month. It knew a latest and earliest possible sunset and sunrise, and from there just calculated out what an estimate of what that day's sunrise and sunset would be. It then would move based on the day. Once it reached its maximum rotation, it would stay there until sunrise and then move the other way and start over again. With the final product in hand, all programmed and ready to go, I started taking measurements at different times during the day. So I took a measurement at solar noon when the sun was at its brightest, and then also later that afternoon and that evening of the same day. So as you can see, I measured the voltage in the amperage, and then from there I calculated the wattage. So from a 0-degree perpendicular arrangement to a 45-degree arrangement, such as you might have at mid-afternoon with a fixed solar panel. The difference on average was about 1.6 times as much power when it's perpendicular. So from there, I could conclude that a single-axis tracking solar panel will generate 1.6 times as much energy in a day compared to a fixed panel. However, the additional hardware upfront costs and maintenance costs negate most benefits for residential systems. Some commercial systems have seen these cost benefits be worth it and are using tracking solar panels. However, the most important factor in aiming solar panels is to aim them based on the latitude. For example, in a northern hemisphere, such as Pennsylvania, panels should point towards the south. Because this does not require moving parts and will greatly increase the energy produced, because the sun is always going to be coming from the south by some degree, this has the largest effect on your solar panel's energy production. Thank you for watching my virtual presentation of my STEM Fair project, and I hope you enjoyed.